Okay, so your exam has been was graded right on the Friday before break. For there were two students who had to take it with DRS, so those students got graded today. So everybody should have a grade. If you received a 0 but you took the exam, if you took it with a TA at a different time. Basically, if you got a 0 and you know you shouldn't have gotten a 0 because you've taken the exam, then you need to reach out to a TA because the only people who get 0s on this exam are people who haven't taken it, right? You should be able to get your exam back in your lectures. Following that, I'll be happy to meet over Zoom to answer questions on that or meet during office hours to answer individual questions about your exam. One thing I will just simply give you a heads up on, and we will not be offended by this, is that be sure that we added up your points correctly. It hasn't happened in a while, but occasionally we make addition errors, right? The most egregious of which happened about 7 years ago, where I accidentally missed, where I ended up having to adjust the student's score by 10 points because I missed a 10 or something like that. It happens. I'm not going to be upset because you pointed out one of my mistakes. If you don't understand why you got a grade on what grade you got on a specific question, please reach out to me. We generally, I gave guidance for all the questions, but I ended up doing a lot of the later questions, especially that last one with the dots. So, if you have questions about that, please let me know. I'll be happy to. If you feel like you should have your answer deserves more questions, that's something If you feel that your answer deserves more points, I will entertain that. There have been cases where I've given plenty of points back to students who have made mistakes. All right. Yes.
We just say we get back in lectures, but
in lab.
So from now on, next time we have a lab, we're gonna get like the papers.
Yeah, you'll get back to your exam and it's yours to keep. I'm not recollecting them. Okay. The only thing I don't give back are final exams, right? Because the mechanics of returning those are a bit difficult. Also because that one's just a bit better for me to have a bit more security over this. This one I just tweak a little bit here and there every year, for the most part, for the questions. So we are actually rapidly closing on the finish of most of the mandatory curriculum for this class. We are currently hitting, in fact, you pretty much know everything you need to know to do for 1068 at this point. What I'm talking about here are tools built into Python that are extremely powerful and extremely useful. And the other thing and so we're focusing on that, then we'll focus a bit more on fundamentals as well as regular expressions, which is a pet topic of mine. On Thursday, I will be going over, please make sure you watch these videos because on Thursday I will be going over dictionaries in more detail, especially as it relates to the assignment. You may, if you've used another programming language, you may have had dictionaries before. They were just called something different. If you were in Lua, they may have been called associative arrays. I forget if that's what they're called in JavaScript. In other programming languages like Java, they are called hash maps or maps. And in Python, they're called dictionaries. At the end of the day, though, they're extremely powerful data structures, extremely powerful tools, and they make a lot of programming questions rather trivial, or interview questions rather trivial if you can apply them. So a lot of times they'll go out of their way to find questions that cannot be trivially solved by this. So that's what we'll go over on Thursday, as well as I will go over the next homework, which is Hawaiian pronunciation. I'll go over that in more detail, but dictionaries are the intended way to solve this homework because it is much more difficult to solve it without dictionaries. What it is that your next homework is after the turtle one is that given a valid Hawaiian word, please give me the pronunciation of that word. For instance, if I give you humu humu nuku nuku apua, then you will give me the phonetic pronunciation of that, which is, as everybody knows, the Hawaiian state fish. But it's a fairly straightforward idea here. Just given something, give me the pronunciation for it. At the end over here, we kind of have the idea of how that should work, right? Aloha gives us aloha. Then it will ask us yes or no, and it will just keep asking for you to advance. I'll help outline this as we do this, but for the most part, I will be testing your program on this word. It's a very short word, keiki. Right. And the reason being is that it's very easy, if you don't follow the directions or don't understand what's going on here, you're going to end up with either keiki or keiki, depending on how you program it incorrectly. What we're looking for is 2 syllables, keiki. So again, I'll go over this in more detail, but at the end of the day, what we want here is a dictionary. Believe it or not, that is our second to last homework. Our last homework will be the pig game, which is a dice game. That's just called pig. It's essentially playing chicken with dice. I know, animal references. And then after that, we will basically be relying on, it will all kind of transition over to the final project. I will give you the set day for that, but what will happen is that for the final project, and this will be somewhere closer to the beginning of April, is that at some point at the beginning of April, you're going to have to give me a proposed idea for your final project. Okay? The idea here is that you will meet with me as part of the lecture, and I will okay that idea. The point of this is to make sure that your project is not too easy, nor is it too hard. Or if it is too hard, then to chip away at it until it becomes manageable. If it's too easy, I generally have ways to make it viable. So that now my expectations for the final project, at least for getting a B, are fairly low. For an A, they're fairly mid, I would say. It's fairly easy to get an A on this project. I like to say you get an A for effort, or for and if you manage to entertain me or fulfill your goals, you're probably going to get an A on that. If for some reason stuff broke and you didn't finish stuff, it might end up as a B or C. But pretty much everybody who made some attempt at their project, not even an earnest attempt, but some attempt at their project and went through the motions of it, nobody scored below 70 last semester on the final project for that. But anyway, the proposal is mandatory. And I hate having to do this every semester because at the end of every semester, I get a student who falls into the auto-fail clause on the final project, specifically auto-failing that final project. The proposal, as I mentioned, is mandatory. If you do not, the final project has 4 portions, what we call preposal, proposal, progress report, due date, right? So, in other words, preposal is just brainstorming and kind of getting and kind of looking for a group. Proposal is when you actually give me the idea. Progress report is basically I'm adjusting our expectations kind of a week out if we need to, or saying everything's going fine. It's just basically checking in and possibly reminding you, oh crap, I have a final project to do. But the point being is that if you have not made a proposal, if you have not come to me with the proposal by the time the progress report is due, then you're just going to get an auto 0. I'm just going to give you a 0 on the final project because you're kind of in an irrecoverable situation. Okay? There's not enough time for you to do basically a month's work of thinking, even if that a lot of that thinking is in the background, and a lot of planning, even if that is kind of, again, in the background in that week, right? It's not feasible. And every time where I've bent the rules and said, okay, I have been extremely disappointed in the product. It is not anything, it's basically, you coded that up in 5 minutes. That's not very useful. I will be, in future lectures, I will go over examples of things to do. I'm currently working on a RimWorld mod as kind of an example project. Modding a game that you enjoy is a viable final project. So it is just, just kind of keep in the back of your head. Do I want to make a game? Do I want to learn how to make a phone app? Do I want to do some web development? Right? Just kind of keep that in the back of your head. If for some reason, though, you're terrified because you have no idea what you want to do, that's okay. If you come to me at proposal day with no idea what you want to do, I will get you an idea. Generally, that will be, hey, make a visual novel, because that allows you to be focused on being creative rather than having to worry about coding. And you can still work on RimPy, right? Visual novels are great. RimPy is great, and I'll go over some games like Slay the Princess and Doki Doki Literature Club that were both made in RimPy. They're both great games, although definitely not for kids. Yeah. Oh, Slay the Princess is one of my favorites of all time. It's great.
Did you know that Slay the Princess actually has a Steam?
Yeah, I've been playing it. It's great. I've enjoyed the added material to that. So let's see. So RimPy is a great solution for that. Doing a lot of modding. I've had people do Minecraft mods. I've had people do Stardew Valley mods. Those are great ways to do it. I've had people make mods for games that I'm not familiar with. So those are viable ways of those are viable projects. And as I mentioned earlier, if you want to actually try making a game from scratch, there are a few different, I'll give you a bunch of suggestions on engines and what to do. But this is your chance to learn either Unreal or Unity or Godot or go something with something crazier, right? It's a good, and the execution doesn't have to be brilliant. Like there were some games last semester, there was one person who made a horror game, which I don't necessarily would say if it was they made a good game, but they made a great atmosphere. They really understood the assignment of making their own assignment of making a horror game and giving it a creepy atmosphere. They did great work with the sound, that kind of stuff. By far, I'd say like one of my favorite final projects of all time was if you're familiar with the game WarioWare. It was very similar to WarioWare. The idea here is that this was not one game, but like 5 micro games, like mash the buttons as fast as you can, or dodge these flying animals. In other words, you were just simply pressing up or down to move. And these would last for like 10 seconds at a time. Very, very simple games, very, very simple, just back to back to back in frequency. And those are fun. Another person used data they had collected on rats in a lab that they were working on, and that was possibly the first time that I was able to. That I looked at a final project and went, I haven't had a final project that involved cocaine before. So, because lab rats get tested on all sorts of stuff. So, it was if you are a senior and you're doing research, or a junior and doing research, or you're just doing research, this is a great way to kind of hook that in. And it's useful because you can find that with a Python script, you're automating something in your experiments that you weren't able to automate, and now you're saving a bunch of time and effort. All right, with that, I've droned on for long enough. What you're going to want to do is go to Module 8 and click on the Tuesday tab. Jeez. The Tuesday tab, or you'll want to go to runestone.academy. So yeah, the Tuesday. So you go to modules, log into Canvas, go to modules, go to module 8, scroll down to Tuesday, and click on the Tuesday, or go to runestone.academy, right? Log in, and then go to, go to the textbook, and this will be one of those projects all the way down in the bottom, which is Project 11, Exploring Common Words and SETI. So today we're going to be reviewing. We are going to be reviewing some material from before the break. I'm also going to be showing off one of the graphing libraries, I believe, in this project, which will probably involve me having to open up an older last year's assignment for Runestone to grab the code that I've copied multiple times there. All right. So once again, today we're going to be talking about something called Zipf's Law, ZIPF. It's a very fun sounding word, Zipf. It's a name, of course, because names are interesting. And what we're talking about is language. So a lot of projects, we want to do analysis on words. That's kind of important considering that large language models, they're all about words and analyzing words. So we're going to do some basic analysis of words here. Nothing as impressive as that, but we still need a data set for words. So we'll answer a few interesting words in the English language, making use of a list of the 5,000 most common words. 5,000 most common words in the English language. This is from analysis that did a word count of 450 million words from magazines, newspapers, works of academic writing, and fiction. And so it's pretty representative of the English language. And what we're going to do is that we are going to basically ask some questions about how common and uncommon some words are. And we're going to look at this idea behind Zipf's law. Okay? So what is Zipf's law to begin with? Okay? It's got a Wikipedia article, so of course it must be something real. So the idea here is that the nth entry is in a list of measured values sorted in decreasing law order. The nth entry is often inversely proportional to n. Or word frequency is proportional to word rank. Basically what it's trying to say, long story short, it's saying a lot of words to say that basically the most common word will occur twice as often as the next most common word. And then that will occur twice as often as the next most common word. And that will occur twice as often as the next most common word. You can see this in the previous sentence that I said by looking at all the mentions of the word the. And every language has its own kind of markers, right? Every language has its own idea of word. For instance, in Japanese, the word des will come up a whole lot, but I don't know enough Japanese to say what the most frequent word would be. It also depends on what corpus of text you use. For instance, if you're looking at if you're going over the first 5 books of the Bible, right, you're going to find a lot more Moses than you're going to find anywhere else probably. Okay? So it does that's why when we do this lists of stuff, it says we grabbed it from a list of a lot of different things, not just one thing, because that would be representative of the human language. Looking at just legal documents is not representative of the human language. It's representative of lawyers. Okay? So this is the file that we have gotten, and this is one of the great things, and this is going to be very similar to how you would do stuff on an exam, which is you don't actually have to download a file and run it, because you can't do that on paper. You're just kind of given the file and told to do it. So here we were given this file, and it will automatically load. It's great. It's called words5000.csv, And you've got this legend here that we'll just we'll just chop that off as we load it in. But here's what we've got. We've got the rank of the word, which is like first common, second most common, third most common, fourth most common. What is the word? What part of speech it is, with the key over here, and I'll go over that in a second. The frequency at which this occurs. In other words, how many times this word was counted. And then dispersion, which is kind of the weirdness, but basically it's saying how spread out is this over the entire English language, or is this more of a word that exists only in certain contexts? For instance, the word fracas, meaning a fight, that only exists in newspaper articles because only journalists use that word. Okay? Similarly, I believe that, RE has a frequency of 15,000, but its assertion is only 0.47 because most people don't use it. RE is typically used in legal writing. Okay? So let's see what we have. We have A for article. So that is the, right? And A. So in other words, things that kind of point to a word and fulfill this role in English that you may not get in other languages. The computer, as opposed to just computer. V for verb, that makes sense. C for conjunction. I for preposition. T for infinitive. What's with that? Well, to versus to, right? To, so it distinguishes between to and to over here, because to is a fairly frequent word. What we're seeing over here is that that this one is the infinitive. In other words, to be, to see, to write, to sleep. That too. In other words, it's kind of part of another verb. Whereas this one is, I go to the store. Not very important here, just kind of showing it. P and D, pronouns. I'm guessing because this is they're the same shape. That's why they use P and D. We have markers for pronouns, though. Oh, okay. So things like, what's marked with a D? This, that. Okay, different kind of pronouns. I guess they have specific reasons for doing that, but we don't really care about those too much. Just know that they exist. What we really care about in this one is, or what we will really care about this one is the word and the frequency. That's really what we care about from this data set. So let's go ahead and play with it. So your task is to read the file and store the contents into 5 lists. So that's our first task. Remember that as you read each line of the file, the line will be represented as a string. Your goal is to split the line into 5 parts and put each of those parts into the appropriate list. Okay? So I'm going to walk you through this because we've had a week off. Okay? So let's go ahead and just recall how we open a file. In Python, that's super easy. We say open Sesame. Well, not Sesame, but instead of Sesame, we say the file name, which in this case is words5000.csv. And rather than copy pasting it, I'm just going to be boring and say words5000.csv. And then we put in then it's polite, although it would be assumed if you don't put it in, it's polite to put in this R for read. Lets the computer know that this is a file you want to read, and we're going to go ahead and store this in data. That's what I'm just going to call this variable data. That's what I like to call this kind of file wrapper as we'll see. Because if I print it out, it says, hey, data is this wrapper to interact with this open file that we have. Next, so now we've got kind of the file open. So we've opened the file, now we have to read the file. And we can do that with one line. Generally, I like doing it this way because it gives me the most control over how I want to iterate through this file, which is I'm going to say lines is equal to data.read lines. One operation. Doesn't do anything because, of course, I told it not, or rather, it doesn't appear to do anything because I didn't tell it to do anything other than do a bunch of silent operations. But if I print out let's go ahead and say lines 0 through 10, the first 10 lines. Right? I get, this is the first line with the legend on it. The second line, which has the, be, and, of, into, have, to. Okay. So what we're going to do here now is that we need to split this up into 5 lists. Basically what we're going to do is we're going to make 5 lists. One for the rank of the word, one that's going to hold the word itself, one that's going to hold the part of speech for each word, one that's going to hold the frequency, and one that's going to hold the dispersion. So we're going to take all 5 fields of this and store them in individual lists. And so index 0 is going to hold all this, index 1 is going to hold all this, index 2 is going to hold all this, and so on and so forth. Make sense? So because I don't want to deal with this, and because this first line will be special otherwise, would have to be treated specially otherwise, I'm going to just get rid of it. So I'm going to do that by doing this. Lines is equal to lines 1 to the end. So this says, hey, I've got lines here. I want to create a slice of it. I want that slice to be everything starting from the first, from index 1 all the way through the end. Right? This gets everything in it except for that first line. So I'm going to create the slice, and then I'm just going to happen to store it in lines. I don't have to store it in lines. I could store it in a completely new variable, something else, but that's where I'm going to store it. Then I'm going to print. So now you can see I've gotten rid of that first one. Next, let's go ahead and create those 5 variables that I need, right? So rank, we're going to create rank, then we have the word, and those are both 4-letter words, so I'm just going to try my best to keep everything at 4 letters just for the sake of ease. Next is, let's see, rank, word, part, for part of speech. And I could put S's on them to say ranks, words, parts, but then freak, and then dispersion. I'm going to go ahead and copy this because I'll need this later for this part. So now that I've got basically my parts of this problem set up, I'm going to read the file, or I'm going to go iterate over the file or the contents of the file for line in lines. And like I said, I like doing this because it makes sense to my brain for singular in plural, right? For line in lines. But for some people, this is an abomination unto the Lord. And, terrible things should happen to me because I did this. So if that's the case, you could do if or L in lines. And that might get the idea across here. But yes.
So what's the task? Like, what's the goal?
The task is to take each of these 5, is to read each line, and for each line, take the 5 fields of that line and store and break it apart and store it into these. Basically, get our data so that we can individually sift through it. Okay? So what we're going to do is that for every line, we are going to we're going to split it up into fields. I'm going to call it fields as opposed to parts like I normally do because I've already got a part variable. So fields is equal to line dot, and because we've got a bunch of commas because it's a comma separated value, that's what the CSV stood for, right? CSV, comma separated value, split on the commas. If we do that operation, and again, I'm going to just do this over the first 10 lines for right now. It'll be a bit easier to see. But rather than it being one giant string, we now have we have this split up into a list of strings, then the next item is split up into a list of strings, and so on and so forth. Okay. So now is what I'm going to do. I'm going to use this. So we split this up into 5 parts. So I'm copying this because while I don't need this, it's indented poorly. So what I've done here is I've selected everything and I hit tab. So that indents all those all at once. So don't need those equals because I've already, because that would be recreating the list every time I took another step and that would destroy everything. No, what I wanted to copy was just simply the word, so I didn't have to retype each of them because I'm lazy. And probably would have taken me less effort to not do that and not explain, but hey. But what we can do now is we can do dot append to each of these, because for each of these we want to add an item. For rank, that's the first thing, so we'd want to add fields 0. Notice I'm doing quite a bit of copying pasting here. Then word was the second field, so index 1. Part was index 2. Frequency was index 3, right? Index 0, index 1, index 2, index 3, and then index 4. Okay? Make sense to everybody? So I've taken this list, I've put it into a list of strings. Then for each string, what I did is I split it up and then took each of the pieces of that field that I split up and I'm adding it to the appropriate list. So if I do print rank and I do print frequency, that's the only two I'm going to do, and I run it, you'll see that I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, because that's what we got going down this file, 1, 2, 3, 4, 5. And then for the frequency, we have 220 as the first 3 digits, 125 as the second 3 digits, 220, 125, okay? And finally, these are all strings, right, that I'm adding to these lists, but I might need to do some addition later, so I'm going to just simply, anything that's a number, I'm going to cast as a number. So ranks are a number, so I'm going to cast that to an integer. The word is a string, so that doesn't make sense to cast. The part of speech, that's a single letter, that's not something to cast. The frequency, that is a number, it's a whole number, so it's going to be an int, right? You can't have part of a count, right? You can't see a word, or ideally you shouldn't be seeing, for your data, you shouldn't be seeing a word 1.5 times. It's going to be once, twice, 3 times, right? And then dispersion, that's a real number between 0 and 1. So that's where we are going to do float. And now, let's see. What just happened there? Oh. Interesting. Oh, and it's not printing out because, again, I'm expecting it to do something when I've told it explicitly, you're not doing anything. I don't have a print statement right now. It just deleted the print statement I did a bit ago. Print, rank, print, word, print, freak. Here we go. So the rank 1 word is the. It occurs 20. Let's see. Let's count. So that's 22 million times. B occurs 12 million times. And occurs 10 million times. Of occurs 1 million and 3 times. Sorry, 10 million and 3 times, and so on and so forth. Okay. So the next part, so as a bonus, I ran across XKC that many of you on liberal arts campuses may enjoy. frequency of the word of the use sustainable in the English text as a percentage of all words by year, which is one of these fun things you can do with large corpuses of text, right? The word sustainable wasn't really used too much in the 1960s, but then as it became more of a concern to do sustainable things, we can see it grow. Specifically, we're seeing it grow like this in a now this kind of graph we call a log graph, because the y scale is not, right? We aren't going from like even amounts. We're multiplying by 10, right? Right, 0.1 to 1% to 10%, right? This goes up in exponentially. Right, so here what we've got is a logarithmic scale. So going up a whole ding goes up, or a whole dot or a whole like grid point would go up by 10%. Sorry, not 10%, but 10 times. So we see here in 2000, it's making up about 0.0001%. Today it makes up 0.01%. And if we just simply print this trajectory out, sustainable occurs once per page. 2061, sustainable occurs on average once per sentence. By 2109, all sentences are just the word sustainable repeated all over and over. This is the issue with, of course, extrapolating data, which honestly you did a much better one for doing this. But I like this one because it is a logarithmic scale, which is what we're going to be, which is what pretty much you have to graph things in Zipf's law as a result. So to kind of get into the swing of things, what we're going to do is we're going to look at the fraction of overall usage of the top 10 most common words represent. In other words, we want to find out, hey, yeah, I've told you that these words are really common compared to other words, but how common are they? So I want you to figure out what percentage of all words do the top 10 most words represent? And then the same thing for the bottom 10. How do we do this? Well, the first thing you need to do is find kind of the total number of all words, right? Which is actually, I'll do for you in one sentence. It's very simple. Total is equal, well, first off and foremost, I'm going to share what I have previously so you can get it. So you can reload the page to just simply grab that code, and it will appear in your timeline as like your instructor shared it at 240-ish. And I'm just going to simply copy that because because you need that to create your data. Okay. Now that we have our data, we can say something like the total number of words that have been counted, right? The overall total, so the number of times I've seen the number of times I've seen be, the number of times I've seen a, this number of times I've seen to, the total number of times I've seen all of those words that that are in the lists is sum of frequency. Sum is very useful. Sum is very useful because it tells us, it automatically adds something up for us. So I can just simply print total. I don't know if it's going to run without me. Nope. We can see that basically the total number of words add up to 91 million. Okay? And we know that of those, the accounts for 22 million of those. So what percentage do the top 10 make? So in other words, you want to just simply sum up, in this case, the top 10. There's a couple different ways to do that, and I'll let you get to that. I've shared the code with you. I'll let you get to that while I get prepared for the next bit. I need a separate login because I need to log in twice. And that's what incognito can be very useful for. Login.
Explain common words in city. I'll be back in just a second for that. Couple more minutes on this one. There's a lot of different ways to do this one. Remember, what you're trying to figure out is your answer should be somewhere between 0 and 100% for both of these. You're looking for a percentage, or 0 and 1, I should say, is what you're looking for. What proportion is the top 10 most common words, and what proportion is the top are the bottommost words. In other words, the words like the to what proportion of the English language do they make up? Particularly long or complicated, but it has been a week for most of you. So don't worry if you're having issues getting to it. 2 more minutes, then at 2:50 I will give the solution. All right. So, for this one, it's actually fairly straightforward. Not, what we want is we want the total usage percentage for the top 10 words in the list. In other words, we basically need to figure out what does this, plus this, all the way through it, what proportion of the entire corpus does this represent, right? And so we need to add those 10 things together. And to get a percentage, the way that works is you take some number and divide it by a total. Say, okay, this is this amount out of 100. Because we're really good at kind of understanding fractions when they're out of 100. Okay, so total is the total amount. This is the total amount of all the words. And so we're finding out how much are the 10 words. Now, most programming languages, you'd have to do something like this. For index in range, and then I want the first 10 words, so 0 through 10, right? And then you'd have to go and iterate over that. Fortunately, we're working in Python, which makes very common operations like this fairly straightforward. If I want a list containing just the first 10 items of another list, I just slice it. So we are going to solve this problem by slicing. Top 10. So what is it asking for? Percentage amount is top 10. So first we're going to go with top 10 is equal to, it's going to go, and we're going to call it top 10 list. I'm just going to say that's the frequency, and we're just going to slice it from 0 to 10, or we could just leave that out, that 0 out, and say from the beginning up to 10. And this gives us a list of all the, and you know what? I'll just print it right here just to show you. Right? The slice gives us, okay, these 10 words. Sorry, these 10 values. I'm going to go ahead and copy this, and I'm going to reload because, yes, spring 2025. Sorry, it did not like me, in fact, logging into a new window. save, run that. So print freak slice from 0 to 10. Run. Right, and here's the first 10, here are the top 10 values, the values that for the top 10 words. And if I just want to add up that total, all I have to do is do this. I have to just tell it to sum it, right? Which I know how to do from the previous line. Was never, oh right, I didn't close it. I make the mistake. 2. And so if we add them together, that's 91 million, which is very close to this number, in fact. That shouldn't be the exact same. What did I miss up? Oh, total. Okay. Okay. Save, run, total. That shouldn't be the exact same numbers. Oh, because I'm only doing the first 10. Silly me. That was just simply to make printing easier. So let's go ahead and see. So the total is actually 329 million. There we go. 329 million and then 91 million. It's when you forget to take the debugging parts out. So what we want to do is just simply put this in a fraction. Put this number above this number, and that will give us a number between 0 and 1. So top underscore 10 is equal to total is our bottom number, and our top number is going to be freak 0 to 10. No. What are you doing? There you go. Type error for list and int. Right. And then we take that total and divide it. Like, I know I'm missing something. Okay. And then for the bottom 10, we do the exact same thing to get the right numbers 4991, 4992, 4993, all the way to through 5,000. We do the exact same thing, only we just do, well, we can do this, okay? Which is, we know that the last 10, we know this is 5,000 long, so we could say start at, I think 499, be 4999. And here's the issue with, and then bottom 10, but this is probably going to get off by 1 error. This is why I don't like doing it like this. Yep, exactly, off by 1 error. Here we go. But that relies off of knowing that this is 5,000 long, right? Which I don't like that. If I want to get basically what I'm trying to do is get the last 10 items in the list. So we're going to take advantage of this. Negative indices. Wonderful feature in Python. I'm going to run it, and then I'm going to go into that for just a second. So, because I don't think I've actually taken the opportunity to lecture on negative indexes in Python, because they're kind of amazing. All right, let's go ahead and create a list. L is equal to list, range 0 to 50. It doesn't really matter, right? I've got a list here, okay? All the numbers from 0 up to, but including 49, right? Now, indexes in Python are pretty cool, for the most part, they work exactly as they do in other languages. If I ask for index 0, it's going to give me the item at index 0. If I ask for the item at index 49. Because we went through 50, there's up to, but not including the 50th index, or index 50, I should say. Right? Goes up to, but does not include 50. And if I ask for index 50, which doesn't exist, right? It's going to tell me the index is out of range. What you may not have tested is what if you did a negative index? Because why would you bother testing a negative index? It's obviously nonsense. L negative 1 is 49. L negative 2 is 48. L negative 3 is 47. The index and the item are the same value here, but we're printing out the value that's stored in the index. So L negative 1 is very useful because that gives you the last item. It's wonderful. In fact, the way to think of it is being shorthand for the following thing, which is what you have to do in other programming languages, because this does come up quite a bit, wanting to get the last thing. In other programming languages, you do it like this. The length of L minus 1 to get the last index, right? 50 minus 1 gets you index 49. 50 minus 2 gives you index 48, right? So you can think of this as being short for that. But negative 1 gives you the last item. And negative 2 gives you the second to last item. Very useful. Negative 10 to the end gives me 10 items. So very useful there as well. And so when I ask for a slice like this says give me the last 10 items. Go from the 10th to last index all the way to the end. Very, very useful. Similarly, if I did this, L, the slice from everything, and then I put a negative 1 here, this says give me everything but the very last item in the list. Right? Or I could do give me everything but the last 10 items in the list. And again, this is not necessarily a feature you need to know, because you could just simply go back to doing something like this. If I wanted everything but the last 10 items in the list, I could just do length minus 1, but it looks and feels clunkier, right? So you can figure it out, but I mean, like, negative indexes are great. I guess that does beg the question, though, of what happens, can you go out of range on the negatives? And the answer is yes, right? If you wrap back around the other way, L negative 50 gives you the index 0, whereas L negative 51, which would go past the 0, gives you index out of range. It doesn't do the whole modular arithmetic thing where it would loop around. And I guess that makes sense, because with negative, you're going from the back. So, anyway, that's enough of that. So here, I'm saying get the first 10 items, get the last 10 items. So over here, we say that the first 10 items, they make up 27% of all the words in the 5,000 most common words. 27% of all those words. Whereas the least common ones make up 0.1%, 100.5% of all the most common words. What are those last common most words, by the way? Let's go ahead and print them out. Print words from negative 10 to the end. Right? Last 10 words. Negative 10 to the end. Run. Censor, laundry, manual, pistol, naval, plaintiff, kid, middle class, apology, till. And if we look at the dispersions for these, we get that example about words. For instance, plaintiff here is 0.88 because you might hear it in legal reporting, in journals and stuff like that. But it's not a common word that you're going to use every day. You're only going to use it in context of court cases, or maybe you're writing a novel that has court cases or something like that. So it's got a fair bit of dispersion, but it's fairly localized. Right? Whereas There are a few over here that are more common. Chemistry, 9.95. Trouble. Trouble occurs everywhere, right? So 0.97. Okay. So a lot of these are, have a fairly far dispersion among documents. Okay. So, yes.
So weird to me. Why kid is so early? Extrovert.
I'm sorry, I couldn't make that out.
Kid meaning child? Why is it rare?
Let's see. So let's see. Which one is kid? Kid verb, as is I'm kidding.
Oh, verb.
Yep, verb. No, that's a great question. It's kid verb. I was like, really? It's that so down there? Yeah. No, it's kid verb, because this cares about part of speech as well, right? Apparently, this document does. A lot of times, to get a sense of this, I'm about to kind of just briefly show you a graphic library called Altair, which is introduced in a previous project. Altair. And what we're going to do, I've already written this program. We're going to read through it, okay? And what we're going to do is we're going to see this pretty much dramatic exponential curve. And what we're going to get is into a bit of trouble where basically we need a log scale to see what's going on. Science tip, log scales are for quitters who can't find enough paper to make their point properly. This is why log scales exist, by the way, because otherwise you cannot graph what you're seeing, right? Fuel energy density in megajoules per kilogram. Okay. And scientists in general, if you do science, you'll find out that if you can arrange your data and it gets into a straight line, that's pretty exciting because that means you can make some kind of conclusion about it. And then, they go totally bonkers if you convert both the y and the axis using base log 10 fraction, and it gives you a straight line. So over here, this is what I wrote last year. Import Altair, import math. Okay, math for using some math functions like the logarithmic function. I'm going to do it without the log function over here first. Okay, we're going to ignore the green lines because they're commented out. Right, we've got the exact same thing here, reading everything but the first line. I just do that here. I just am lazy and do the entire first few lines, like this bit. I just kind of do that in one line over here. Like I said, that can make readability a pain sometimes, but it made it more succinct. We split up the line and we add them like we had been doing earlier, so this is exactly the same code. Okay? What we do with Altair is that enables us to kind of say, hey, I'm going to make these keys called ranking and frequency to correspond with rank and frequency. Those are going to be our data. I'd like to chart that data, and I'd like it to be made by marking a line, and the X is going to be ranking, and the Y is going to be our frequency. Then please display it. Okay. You can look into more details as to how this works, but math is imported but not used. That makes sense. And so what we are doing is we're plotting the rank of the word against against how frequency it appears. So the is all the way over here and it appears 22 million times, so it's up here. And you can see that this is a fairly useless you can't even see it's a fairly useless graph because it's basically just kind of except for here, is outlining the axis of the graph. This is a fairly useless graph except that it tells us that it needs to be in log. Basically, what we're seeing here is we cannot parse the data easily enough to get an idea of what we're looking at. So this is where basically doing logarithmic calculations comes in. Now, logarithms aren't as scary as you think they are. First off, I'm going to give you even though time is limited, it's valuable enough for those of you who never take a class with me.
again, for you to learn the way logarithms really work, at least from the perspective of somebody who uses them to do operations rather than mathematical theory, right? Because you've been taught some awful theory about this. Log of base B of A is equal to C, right? And that corresponds to let's say, what is it? B, let's see, B to the Cth power is equal to A, right? That's how, you've learned that. It's nonsense. That's boring. You don't understand that. Other than that's a relationship. Here's what something tells you. And we're going to use log base 2 because computer scientists love log base 2 because binary stuff. Okay, log base 2 equals whoops, I can't spell today apparently. Splits. That's the number of times you can split something, specifically splitting it in half. Let's take a look. Log base 2, let's take a look at 64. How many times can we break this in half? We can break it into 32s. We can break those 32s into 16s. We can break those 16s into 8s, right? We're just simply continuously breaking the numbers in half. We can break 8s into 4s. We can take those 4s, we can break those into 2s, right? And then we can take those 4s and break them into 1s. So now the question is, how many times did I break it up? 1, 2, 3, 4, 5, 6. I broke it up 6 times. Thus, log base 2 of 64 is 6. Note the lack of math involved other than just dividing by 2 constantly. It tells me how many times I can break this in half. That's what it effectively means. How many times can I break this in half? Similarly, log base 10 of 1,000, and this is just, again, log base 10, okay? That's asking how many times can I break this into tenths? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many times can I break this up? I can break it into 1,000 into 10 100s. I can break up those 100s into 10s, and then I can break up those 10s into 1s. Because we're looking in base 10, we're talking about tenths, or how many times can I break it? Can I split it up into tenths? 10 parts. I can do it 1 time, 2 times, 3 times before I get down to 1. Okay, now obviously this metaphor fails if I'm like trying something like trying to do this 1,001, right? Because now I'm suddenly not able to split things evenly, right? But now you know that the answer is probably a little bit more than 3, and you know why that is, because you're going to take something and divide that over a bunch of things. Similarly with 65, right? It's going to be somewhere over 64, but a lot of times in computer science, what we're looking at when we're talking about logs is that we're asking, how many times can I have something? And that's sometimes a lot more of a useful way of looking at things than just simply a very, honestly, elegant equation or a set of equations. Okay, so I've went ahead and turned not the rank, actually, we don't want to do the ranks yet but I'm going to take the frequencies, okay, and I'm going to put that into base 10, okay? And now we get something a bit more doable to work with. We can see some amount of data. And what am I looking at? What I'm looking at is these numbers now represent 10 to the 0th power, 10 to the 2nd power, 10 to the 4th power, 10 to the 6th power, somewhere between, and this is somewhere between 10 to the 7th and 10 to the 8th, right? Why? Because remember, one second. This occurred 22 million times. So a million is 10 to the 6th power, so 10 million is 10 to the 7th, so this is a bit more than 10 to the 7th, so that's why it's over there. And we see that basically that it's decreasing very rapidly. There's very few things that had a count of over 1 million, and then we rapidly get into a lot of things that were in the hundreds of thousands, but then it seems to crater in the 10 to the 4th. Tens of thousands is where we occur. now we're going to go ahead and do the other part. We're going to go ahead and turn the y-axis into a log, which, just to see if that does anything for us. And it does. It does. It gives us this kind of more, much more of a line. But let's go ahead and just kind of look at Zipf's law for a second. So here I'm going to change this 10 into a 2. Why? I've never done this before, by the way. Why? Because log base 2, again, is how many times I can have this number. So now I'm just turning the y-axis into powers of 2. Did I? That doesn't seem to be right. Log in 10 base 2. Is that how I do it? Oh, yeah, that's not going to do anything because that's the because that's the x-axis, of course. Silly me. So base 2, not base 2, 10. That'd be rather ridiculous. Okay, y-axis is now base 2. And so what we can see here is by base 2, and basically every time we would go down a number, that's it occurring at half as common as the last value. So basically the difference between 19 and 20 and on the axis is that 20 occurs twice as often as 9. And we see this relationship basically that in Zipf's law, the kind of idea here is that we see that the most common word occurs approximately twice as often as the next common and 3 times as often as the third common, and so on. For example, the occurs the most frequently, 7% of all word occurrences. But we can actually just look at our data, okay? We can just kind of look at our data. 1 second. Where's our data? It's in a different tab, of course, because we are, right? We can just look at our data and see it that this number, the is about twice as big as this number. And I wouldn't say it's necessarily 3 times as big as these numbers, but it is close to 3 times as big as number 6, which is 70,000. That's approximately 22 is approximately 3 times as big as 7. Approximately, right? It's approximate, right? 7 times 3 is 21. That's close enough to 22 for if we squint at it. But the idea here is that this general trend of data works out. So it's pretty nifty. There's a number of graphing libraries. Altair is not necessarily my favorite, but it is embeddable into the web browser, which is pretty cool, which is why we can use it here. I'm just going to go ahead and share the code with you so you can use it. Okay? Next, we can, so you'll be able to reload the page. If you are graphing stuff in Python, and I've used this on scientific papers that I've published, okay? Which is not as big of a flex as it sounds, to be honest. Matplotlib. This is the premier Python library for graphing. It creates all sorts of fun graphs that you can do. It even has an XKCD mode. It creates CQuiver. It can create graphs like this. It can create plots like this. Any kind of graph or diagram of data you need, it's there. It's going to be there for you, given that you read the documentation, which is its own special hell. But programming, you're already programming, so that's just more of the same. But it's great. It's great. It also makes use of this other library called NumPy, which is one of the big math programming libraries out there in any kind of statistical work. So if your final project involves doing analysis of data and you want to stick around in Python, then this is worthwhile knowing. If you're doing statistical analysis, by the way, the other programming language, and I emphasize language as opposed to like something like SPSS, I think is like an application. If you're looking at a language to do heavy math lifting, specifically statistical work, Erlang, specifically the R programming language. This is specifically a language designed for scientific computing. I cannot write in it, but I can read it. I've helped debug projects that use R.
It's funny that once you start programming, you can like debug languages that you've not seen, even though you couldn't write any of it, because because mistakes show up no matter what. You forgot a comma, you forgot to close a curly brace. Those kind of things are universal, and people are gonna make them, and don't fret about it. All right. So on Thursday, again, please watch the dictionary stuff. I'm going to go because I'll do a brief overview of those dictionaries again, just to review the material. And then I'm going to get you started on the next homework on Thursday. I'm going to do a nice chunk of it in class so that you are going to be nice and ready for Friday and Monday's lab. Okay? All right. I hope you all have a very pleasant day. And I hope that transitioning back to school after that week-long break isn't too rough.